today also I would like to give you some kind of exposure on some recent interesting applications where this AI and the brain signal communication, those parts are which are basically forte, my forte. So basically, I'm going to give you the another kind of interesting problems where we can address AI, because all of us, we know that AICT has been designed, yeah, and such curriculum, and it is basically coming up with all these nine emerging areas where basically AI and robotics falls. So basically, on this positive note, I'm going to start today's presentation, and I'm going to start this presentation by presenting my screen. So all of you just give me the feedback that whether you can, you know, whether you can visualize the screen. Is it visible?
Yes, ma'am, it is visible.
Okay, okay. Thank you, thank you, thank you very much. Okay, so first of all, today's presentation, today's topic of discussion, or should I say that now we have emerged your sense of interaction between from both ends, because we have done one lecture session already, so we are quite familiar about some concepts of artificial intelligence in the the last session on Monday, I suppose. Professor Shunchita, uh, she has given a beautiful presentation on how the learning procedures are all about. How does a particular object in artificial intelligence be labeled as feature? How a particular object, or how a particular stimulus can be detected by identifying its right features, right characteristics levels, how this can be labeled. So in this today's uh, discussion, I would also like to highlight in some particular point where we can take feature and classifier as a particular problem in, or as spatial attributes in artificial intelligence, to basically deal in certain specific AI related problems. So today, this is all about artificial intelligence in t-taster selection. So all of our, I must, believe that all of you have heard about tea tasting, right? This is a, a very, interesting job, So what we here did basically, we had, contacted a handful number of, tea tasters, and we have designed a particular, AI related, design algorithm, so that we can, find that the potential tea tasters among a handful tea tasters, or you can say a bunch of tea tasters. So because why this is so important, why this is why we have come up an idea to basically address this particular area, because we had a large vast of region in the Assam, in the Darjeeling side, where basically we boast of about some good aromatic tea leaves, right? So basically, to identify the quality of tea leaves is very very important, because when we feel that, I mean, how much this is important, that we feel whenever we are going to sip a cup of tea, you know in the very morning, right? So basically, that in that very manner, we have developed an idea that why don't we use some kind of artificial intelligence techniques, so that we can identify this kind of selection technique, which basically which can help us in our to day lives, which can enhance the selection of the quality tea leaves, right? And that those quality tea leaves can come to our drawing room, or you can say the living room, or you can say on the dining table, or you can say in the balcony, where we are going to enjoy the sip of tea. So, this is first of all the today's topic of discussion, and let me introduce myself. Myself is Dr. Rumrata Shaha. I have met you all on a Monday. That was my first session with you, and this is the second session of this FDP, and I'm going to start today's topic. So this can be, a kind of workflow whenever we are going to, decide to basically address this particular problem. That is, we are going to select tea tasters. So first of all, if you can recall my previous, lecture, then basically there must be a kind of, workflow, must be a kind of, flow chart, that how we are going to proceed, in this particular, any kind of, problems, or I can say that any kind of, problems which basically, consist of, brain computer interface. So yes, obviously it is also a problem of brain computer interface where AI, artificial intelligence, is incorporated. So first of all, what we need to do is we need to identify the sensory information. About the sensory information, that means that, in the previous session as well, I have discussed that sometimes what happens that if I want to establish one brain computer interfacing, then obviously we must, need some kind of, inputs. We must need some kind of inputs. And those inputs are, either coming from the environment, or you can say that those informations are coming from the, PCs and or laptops as well. So whatever be the information, that information must be related to any of our sensory organs, or or should I say that not only one, maybe there could be, the involvement of more than two sensory organs, right? So that we can, work with any kind of, multimodal, you know, problem, that where we can see that more than, one or two sensory informations we are required. So here also, for this particular problem, we should identify first of all what is the sensory information, right? Whether it is associated with my auditory nerves, whether it is necessary, it is associated with my visual information. What could be the sensory information here? After then, whenever this identification part is over, then obviously there is some, a point where we need to establish the relationship between the sensory information and human perception. Why it is so necessary? Because as you can see that all tea tasters are humans, right? So automatically all those sensory information must be processed by some human persons. So automatically that humans must have some kind of perception, or this human can, must be able to perceive those kind of sensory information, so that he or she can be able to, to process those information further using the brain computer interface. So obviously we should know what is the relationship lies between this sensory information and this human perception. When these two groundworks have been completed, now come we are, slightly proceeding to our, experimental section. So before starting our experimental section, first of all, what we need to do is we need to locate our brain lobes, right? Because we have done the previous, session, and we know that we have, certain major, brain lobes, which are basically, what should I say, which are basically informative, or which are basically responsible to perform certain cognitive, tasks. So automatically we should locate the brain lobes, the exact brain lobes from where we are going to collect the brain signals to basically to process those one. And whenever these brain lobes are being detected, and obviously these brain lobes are, associated with some kind of, cognitive task, so obviously there must be, an association of EEG band of frequencies. That means whether it is associated with delta bands, whether it is associated with theta, whether it is associated with alpha, or like that. That means what are the frequency region from where we are getting those EEG signals. I can remember that in previous session, one might have asked that he must be, facing some kind of, problem for, denoising of EMG signals. So there also I have mentioned that this is a kind of, problem which we generally, uh, uh, encounter whenever we are going to work with this brain signals or the muscle signals, because this, the filtering is very very important, right? Because you need to choose, such kind of, passband frequencies for your design bandpass filters, where these passband frequencies must be, associated with your EEG subband frequencies, so that you can get the exact ideal EEG band of frequencies from that very location where your cognitive task, where the brain signals associated with that particular cognitive task is basically liberated. So this is very very important, step for this work process, that is locating the brain lobes and EEG bands of frequencies. If we miss to perform this particular, step correctly or accurately, then we may miss the exact, the original, the right EEG signals, which basically are pointing, to that particular, cognitive task. And we may gather all the noisy data, which basically, is of no use. So basically that is why the data acquisition of this brain computer in any kind of brain computer interfacing, experiment is very very important, the step. After this, after when you complete all your, survey of the sensory information, of the relationship between the sensory information and the human perception, identifying the brain lobes, identifying the frequencies, now you are perfectly ready to design the problem, that how you are going to perform that particular problem, to address, or to, to address the solution of this problem. And there lies the, the remaining steps, I can say, for this workflow. That is, first of all, obviously EEG signal acquisition must be done. Then obviously whenever you have gathered your EEG signals or brain signals, through this electroencephalography, which is a full form of EEG, then obviously you need to identify the correct features and what are those, and how these are, happened. I am just going to, talk into details whenever I move to the further slides. So first of all, from the signal, you need to identify those attributes which basically belong to a particular, object, or which point it out, a particular, object, or a particular, stimulus, I can say. After then, whenever you have your right features, then the job is to design a particular robust classifier. So automatically, what does this mean? This means classify means now I need to classify, or I need to, segregate between two or three input patterns, right? Input, or I can say three or four input classes. So basically, to design a classifier enhances or ensures ultimately the accuracy, or the, I can say, the correct, identification of the input class. So designing a robust classifier, that is also a very important, phenomenon in any kind of, brain computer interfacing or artificial intelligence or pattern recognition kind of, problem. And then now whenever you have got a handful, results, then automatically you can, easily you can comment on the performance of your own classifier with the standard ones, that means with the existing ones, with the traditional ones, right? So you can compare the performance of your own classifier with the standard classifiers, and now you can formulate now easily one metric. You can design a particular metric which basically gives you the perceptual ability of a human person. That means automatically, if we want to, find out the exact right, t-taster, we need to, go into checking the perceptual ability of that particular t-testers. So we need to formulate something metric, and automatically we are now ready to test on, t-testers. So this is all about the workflow. That means, before testing on the t-testers, we need to, train, and we need to, go on testing on, a large number of, data sets which are basically, collected from a large pool of human subjects, because obviously t-testers are very few, and we cannot, afford to, make them by sitting and giving, data for hours and hours and days, right? So basically we need to do first that groundwork, pre-hand, and then if whenever we are very much sure about our, innovation, then we can use this particular thing on the, t-testers to test the results. So this is the workflow of this, what should I say, the t-taster selection problem using artificial intelligence. So whenever we have this workflow, now we are, are able to start with the perception. Why this is perception? Because obviously whenever we know that this is a kind of, tea taster selection, that means automatically it must be, associated with some kind of smell, right? Some kind of aroma of tea leaves. So basically, out of all these perception, that is auditory perception, visual perception, olfactory, taste, tactile, our this problem, falls, under this olfactory perception. So that is why this perception is nothing but, to understand and interpret external stimuli, what you are fed from outside of the environment. And obviously, and perceptual ability of any human subject is nothing but the ability to basically recognize and to interpret that stimuli with using, or I can say using, their own sense, right? So, or in on their experience, on their knowledge. So this is all about, perceptual ability. So whenever we have, identified that this particular problem, falls under the olfactory perception, that means now we know that we need to, process our olfactory signals. That means the brain signals which are going to be liberated when you, or, you means any person or any subjects, when those subjects are experiencing any kind of aroma, right? So basically, whenever this particular thing has been detected, that we are now going to, offer, or we are now going to, deal with some kind of, brain computer interfacing problem with olfactory signals, then we should know what are the brain modules, right? So this is, a very familiar, slides, those who have, attended my previous session, that these are the brain modules which we know all about. But here, in those, I mean, with those brain modules, what we hear is we get, and or what I say that, what should I say that I need to focus on prefrontal region. I need to focus on prefrontal region, which, in last day I have shown you that these are the, this region, that is the forehead region, is the prefrontal region, which is very, very, important, and which plays, a very major role to basically process the aroma whenever the aroma is taken, or is sensed by any human subject, because we know that the nostrils, which is the nose, is basically, in the front of a side, or is in the right alignment of our, forehead. So this is prefrontal region, which basically, falls under the, obviously, the, or under the frontal lobe. That is why we, you know refer here that this is a region which basically comes under the frontal lobe, and this is the prefrontal region, that means the region, on our forehead. Fine. So whenever this is sorted, now automatically we should come to the brain rhythms, which basically are, going to be important for this particular problem. So we know that we have, this kind of, five brain rhythms, and we are very much associated right now that those are the frequency, regions, and those are the significance, about each and every, brain rhythms, and we have discussed this, previously. So here, in this specific problem, that means in the problem of olfactory, perception, there basically these two rhythms, you can see, that is the theta rhythms and the alpha rhythms. These two rhythms, which are having the frequency of 3 to 7 hertz and 7 to 13 hertz. So combiningly, I can say that the 3 to 30 hertz, from 3 hertz to 13 hertz, is our primary, important area of frequency, which basically deals with this kind of, problem, where a person is alert but not physically active, but obviously these are relaxed, some kind of problem solving or some kind of decision making, performance that particular person is giving. So basically you can see that whenever we are, going to, smell something, we are going to smell something, and if you are ever asked to basically to give a comment on a flower, right? Let's say you are given one, at one particular point of time, you are given rose, right? And at another particular time frame, you are given jasmine. So basically this rose and jasmine, are having different smell. So if you are asked to basically judge, or to basically comment, or to basically decide that which one is rose and which one is jasmine, only by, experiencing your, through your aroma, and you are not allowed to see those flowers, because, if you can see that particular flower, even if it is jasmine, even it is rose, then automatically what happened, that your visual, processing, your visual signals, will give you certain, decision. That is, yes, if I see a particular rose, so automatically we should know how rose, looks like. So I can automatically, confirm that yes, this flower is rose. And if you are given jasmine, and if you are allowed to see jasmine, then you can automatically, comment that yes, I know that this flower must be just jasmine. But if you were allowed to, only, dependent on your aroma, not, and you're not allowing to see the flower, then automatically you should go on this, right? You are going to inhale the smell, inhale the aroma by your making your eyes closed, and whatever be the aroma you are experiencing, based on that aroma, you are going to judge whether this smell is of rose or of jasmine. Now, how can you make this particular decision? Tell me. That means there must be some kind of, synthesis is going inside your brain, that the brain signals can detect that this particular, aroma is of rose, this particular aroma is of jasmine, because you are not, looking at any flower. So there lies the beauty of our brain. There lies the beauty of our learning. So in the previous lectures on which were going on Monday, which were going on Tuesday, there also you have heard about lots and lots of, learning schemes. So this is a kind of human learnings which basically we learn from our childhood, that if you smell like this must be the smell of rose. If you smell like this is the smell of jasmine. So automatically there must be some kind of information stored in our memory, stored in our brain, and brain can react in that particular, in fact, that particular way, or the brain can reciprocate in that manner, that whenever it feels, it senses a particular kind of, signals, a particular kind of, aromatic, synthesis, that brain is automatically giving you the decision that this is a particular, flower, rose, which is, offered to you. Now there lies the problem definition. That means we need to analyze the brain signals right there whenever a person is offered rose. That means what are the, EEG signals, and those brain signals are going to be collected through electroencephalography device, so that we can process those signals to basically, come up as a pattern classification problem, so that we can say that this is some kind of pattern where, I mean, which is associated with the aroma of rose. Or I can say that this is a kind of, pattern which can be associated with the, the aroma of jasmine. And let's say classify those patterns, those set of patterns, and we can, come up an algorithm, and obviously the some kind of, innovation, which basically, which enables us, which tells us that yes, this is, the flower rose, and this is the flower of jasmine, without the fact that we are not, watching that particular, or observing that particular object, but only our EEG signals are going to, decide this. So this is the problem definition, where you require these brain rhythms, that is the theta and alpha rhythms, which basically needs you, which is basically needed whenever you are dealing with this olfactory perception problem. Now, if those two things are, again sorted, that means we have decided what are the brain locations, we have decided what are the frequency regions, what are the frequency bands we are going to, work with. Now we can design our experiment. So what does this particular designing, involves? That involves that we are going to, we are going to, get the smell stimulus. Smell stimulus means, that means you can see here that a person, that a subject is, is offered some kind of, smell, some kind of aroma, which is basically taken into a glass bottle. And obviously this is, you can see the bottle size is very small, so that it, it conserves the particular aroma, with its right intensity, so that whenever we can, open up that bottle, and that person, easily can smell those, aroma. So basically these smell stimulus are offered to a particular human subject. You can see here our subject is not watching what particular, aroma you are offering to, right? So this smell stimulus, whenever it is offered to a particular subject, then the receptor neurons in olfactory epithelium of the particular subject are basically, catching those aroma. They are trying to, get into that particular smell, and whenever these receptor neurons are getting this particular smell, those aroma are going to process through olfactory nerve, which basically resides under inside our nostril. And what happens that there is a kind of encoding and perception in human brain, and those encoding involve some kind of synthesis between that organic, between that aromatic stimuli, aromatic synthesis, aromatic components, and also our brain signals. So there is a kind of encoding pattern and encoding process which is going on inside our brain. And humans can perceive a a particular or a specific aroma whenever a particular stimulus is given to her. Whenever this process is going on, then what happened that we have here applied a kind of different EEG device, what I have shown you in the previous session, that we had in the previous problem. We had used a standalone EEG device. Here we have used an wireless EEG device, right? So in this case, this wireless EEG device, you can see there are two electrodes. I will show you this particular picture later on. So this is a kind of uh, two electrodes, two EEG electrodes, which are located in the prefrontal region of this human subjects. And I mean, out of all the regions, this is a wireless EEG headset. So there are plenty of the situation, plenty of the locations from where if I place the EEG electrodes, which are made of AgAgCl. So
Ah,
then we can collect all the EEG signals simultaneously if we want to. But we want to process those EEG signals which are coming, which are liberated from the prefrontal region. And whenever we are taking these particular EEG signals which are coming from the prefrontal region, then we start the process inside our computer. So this is a part which is basically associated with our brain. These are the parts which are basically associated with the computers. Now we are starting with the you know with the inherent or with the fundamental steps which basically involves basically inside the brain computer, any brain computer interfacing problem. That is, we need to filter this particular signals, obviously using some band pass filters, which is having the pass band frequencies of 3 to 13 hertz. Then after filtering, we need to identify the correct features, and we need to select the most significant features from this filtered EEG signals. We can if we found any kind of large data points, and if I found that after after classification, if I found that I do not get a correct smell class, I if I get more than the misclassified class, then I can go for any kind of data point reduction technique as well. The similar process where what I have performed whenever I need to select significant, most significant features. So automatically, what should I do here? We did we did select a few significant features from a large pool of features. So in the very similar manner, we are going to select few data points with a large pool of data points, so we can also reduce the data point as well, so that we can deal with a a feasible data matrix. And then we can classify this particular smell stimulus, so that we can obtain the correct smell class. That means if I offer a particular subject you know like naphthalene, then automatically our motto or our goal is to find out or is to design this process so correctly that our classifier, give me the final result that yes, this particular, you know, stimulus is basically, falling under the naphthalene class. Fine. And this is basically is going to be, detected from our EEG signals, but not visually, right? So this is how we can design the, experiment. And whenever we have designed this experiment, now we can get to know that this is a kind of, what should I say, that this is a pattern classification problem. That means I have, 5 or 10 different, smell stimulus. That means every smell stimulus has its specific pattern. So what can I say, that let us consider that we have taken, naphthalene, we have taken clove, we have taken cardamom, we have taken bay leaves, right? So if I say that these are my different smell stimulus, that means automatically all those smell stimulus, or all the individual every individual smell stimulus has a certain specific pattern, right? So we need to, classify this pattern, and we need to label those input stimulus into such a way that our, our classifier should give me the final result that yes, this particular, output, points at this particular pattern. So patterns are going to be classified finally. So this is, a kind of problem which is called pattern classification problem, which is nothing but to address a particular, a mapping, function, or I can say a kind of, mapping pattern, from the input to the output for given set of training instances. What is that? That means if I give input, if means features. If I give input features of what? Input features of, let's say, first smell stimulus. Let's say it is, naphthalene, let's say. So basically, if I give the naphthalene, if I offer, the aroma of naphthalene to the human subjects, then whatever be the, EEG signals that is liberated from the human brain during this process of inhalation of the naphthalene, that is being collected, and that is being, from that particular EEG signals are basically, I can say the filtered EEG signals, all the features are basically going to be extracted, and those features are fed to the pattern classifier. Now, let us assume that I am giving particular uh, human subjects, naphthalene once, right? Naphthalene once. Let's say that, and obviously I am giving this, aroma. I am giving this, particular, smell stimulus for a time duration. Let's say for 30 seconds, right? So basically, for 30 seconds, this electroencephalography device is, capturing your brain signals, right? So automatically during this 30 seconds, depending on the sampling frequency of that particular device, I should get how many, I should get a, a specific number of, samples within, those time frame, because sampling frequency, we all know that the sampling frequency is nothing but, that gives you the number of samples within, 1 second. So if I now, use that particular, any particular device which is having, let's say, in sampling frequency, in hertz sampling frequency, and if I use that particular device for, let's say, 30 seconds, so automatically, this 30 seconds duration will capture, so much samples, right? So this is all about your EEG data, raw EEG data. Out of this raw EEG data, first of all, you should do the filtering process. You should design a particular band pass filter with having the passband frequencies set by your own, and whatever be the filtered frequency, filtered EEG signal you are getting from those EEG filtered, from those filtered EEG signal, you are now basically going to extract those EEG features. Let's say you have extracted capital N number of features from this filtered EEG signal, right? So if you have this n number of capital N number of features for one particular instance of giving naphthalene to the human subjects, then let us assume that these are the feature values you are getting. If you look at the first row, that is, let's say f1, that first feature f1 is 10, f2 is 20, and it goes up to capital N, and you are receiving the feature values of 80. You can put these feature values in a row, and you can label that particular class, that this can be labeled as class 1. Fine. This can be labeled as class 1. Now what happens that whenever you have this kind of feature values, this is recorded as one instance of having, with one particular smell stimulus, or let's say first smell stimulus. Then again you are going to perform the same experiment, right? Same experiment with same smell stimulus, that means with naphthalene again. After 30 seconds of the second instance, let's say that you are having, after filtering and after feature extraction, you are getting again capital N number of features. And now let's say you are having the feature values of 11, 19, 79, and so on up to 79, right? Now, if you closely observe that, you can see that this row is also, the is denoting the feature values whenever the naphthalene is given. So you can see that those two rows are having very closer feature values. Why? Because obviously all those EG features are basically pointing at naphthalene class, right? So this is, you can do this particular experiment with naphthalene, let's say for 100 or 200 times, and you can form the particular data set or training instances or testing instances, I can say, that even if this is better called training instances. So training instances for naphthalene. This is your one part, one with one smell stimulus is over. Now coming to the second smell stimulus. Now you are planning to offer the human subjects with clove. So it is exactly the different smell what she has just experienced with naphthalene. So now you start the similar kind of experiment with all the similar time frame, that is for 30 seconds, and you are offering to her the smell of clove. Let's say now you are getting EEG feature values of 70, 60, and up to 25. Can you see that these numbers are much different, than what we had whenever we had done the experiment with naphthalene? Because this is very much different, the smell stimulus is very much different what we offered last time. If you go on experimenting with clove for more than one times, you will probably get the EG feature values of like this, which basically has a very which is having very closer feature values of between each other. But all these are falls under another second another output, which is basically giving you the different output what we had last time. Now if I just only limit this particular problem with only these two smell class, I can say that this is my two class classification problem. We have two patterns and we need to classify those two patterns using a pattern classifier. And from there, for their, you know, designing point of view, we can, design, a particular solution for this output, that is this y equal to some kind of, function of f, where this function is called discriminating function. So what we need to, have, so this f is nothing but all the feature values, right? From starting from f1, then coming to f2, f3, and up to fn. And this will give you, either output 1, which belongs to class first class. Let's say this is class 1, which is basically the class of naphthalene. And if this output is giving you the 0, then it belongs to the second class, that is class 2, probably the class of, close. So this is how a pattern classification problem is designed, and you can address or you can deal with this kind of problems even if you have two class classification problems. I have shown you, I have given you the example with two classes. Now, if I, you know, extending the number of classes. Here in our problem, we did so because we cannot ensure, the olfactory perception only by having only two aromas, right? Only two aromas. So this could be a kind of, biasing situation. That is why we need to take, at least, five or at least, 10 different kinds of, sets of aromas, sets of smell stimulus. And that is why we have, multi-class classification problem. It is not, restricted into only two class classification problem, right? So this is how we are going to deal with multi-class classification problem. Now, whenever we have multi-class classification problem, now the problem is every time all about the designing of the final, deciding factor or deciding box, I can say. So final deciding box is nothing but the classifier. So we can have either linear multi-class classifier, or we can have, some kind of, non-linear multi-class classifier. But this should be, multi-class classifier, not two-class classifier. So you can easily see now here we don't restrict the outputs between two classes. It is more than two. It is basically three here, right? So now the concept is, now if this is not the simple case of deciding only zeros and ones, how can we, design this classifier? And if you can remember, previous sessions of, some eminent, speakers we had on Monday and Tuesday, they there, you know, you know gave you the exposure of some kind of, linear classifiers, some kind of, machine learning, which basically involves in machine learning problems, or you can say any kind of, support vector machine classifier, or some kind of, non-linear classifier, or some kind of like hyperplane, or some kind of this. So here I'm going to give you a, a short essence that how this linear classifier, multi-class classifier is being designed, that now we are not, in that particular, situation where we are going to have only zeros and ones. So basically, if you design only one hyperplane, or one, decide, what should I say, one discriminating function. So basically, based on only one discriminating function or one, hyperplane, you can easily, segregate, or you can easily classify, you can easily clustering some kind of data and at the one side of the hyperplane, and you can, segregate the, or you can place the remaining data on the other side of the side, hyperplane. So this would be your two class classification problem. But if you have more than two class, then automatically we must need another function